All right, in this section, we're going to talk about the physical interpretation of the mean value theorem. So the most popular topic for calculus is to talk about applications to speed. And that's what we're going to do here. So physical interpretation. We can think of the number f of b minus f of a over b minus a. Remember, that's the slope of the secant line, as the average change of f over the interval from a to b. We talked about that in week 1 and 2 of our course. And f prime of c as the instantaneous change. We've talked about that many times as well. Then the mean value theorem says that the instantaneous change at some interior point is equal to the average change of the entire interval. Let's do an example to help you understand. If a car accelerating from 0 takes 8 seconds to go 252 feet, what's the average velocity? Well, you calculate average velocity by doing distance over time. So 352 feet over time of 8 seconds gives you 44 feet per second. That's your average speed. Okay. Now, the mean value theorem says if this is your average speed, then at some point during that time, you had to achieve the exact speedometer reading of 44 feet per second. Think about this. When you talk about average, an average is the middle value. So if you start off accelerating from 0, then you're going 0 miles per hour. So that's going to really bring down your average speed because you're going no speed, you're not traveling any speed at all. Whereas as you speed up over those 8 seconds, in order for your average to be a 44, you have to go over the 44. To go from 0 to somewhere over 44, you have to cross through the speed of 44. This is a continuous change in distance. The function representing distance, your position function, is continuous, which means you have to cross through that value that's your average. So hopefully that helps you a little bit. If not, go hop in your car and drive from the parking lot to your house and say, my average was this speed. I had to achieve that at some point. And think about it. Did you ever hit that particular speed? It's kind of a cool problem to solve. All right, so let's talk about some consequences of the mean value theorem. So this is called a corollary. It basically follows from the theorem. So it was a hey, cool, this popped up in the theorem when we were proving it, and now we could share it with you. It says, if the first derivative of f equals the first derivative of g at each point x in an open interval a to b, then there exists a constant c such that f equals g plus the constant c for all x in the interval from a to b. That is, f minus g is a constant function on a to b. Now, what are we going to use this for? Well, let me talk about this example here. Find the function f whose derivative is sine of x. So if I give you the derivative of your function is sine of x, this corollary says you can find the original function. Okay? Well, use what you already know. The derivative of what function gives you sine of x? Well, I think it's something to do with cosine, isn't it? Well, let's try it. If I have cosine as my original function, what's the derivative of cosine? That would be negative sine of x. Okay, so I'm close. This is how you think through it. You get close and then you adjust. All right, what if I put a negative on the cosine? So the derivative of negative cosine, well, the derivative of cosine is negative sine, and then this negative makes it positive. There you go. That is one possibility of what we call the antiderivative of sine of x. But we have another possibility. For example, if I say f of x equals negative cosine of x plus a number, maybe 5, would that work? Yeah, because what happens to the 5 when you take the derivative? It goes away. It turns out there's an entire family of functions that are the antiderivative. We'll talk about this more later. This is the introduction to antiderivatives. The antiderivative in general is negative cosine of x plus c. This c is going to be something you see a lot. This creates the family of antiderivatives for the function sine of x. Now we want the particular one whose graph passes through this point 0, 2. So not necessarily negative cosine of x, not necessarily negative cosine of x plus 5. We want the one particularly that goes through 0, 2. So this is your x and your y value. What you do is you plug them into the one with the plus c, and you can solve for your c value. So y is 2, that's on the left, equals negative cosine of 0 plus c. What's cosine of 0? 1. So 2 equals negative 1 plus c. Bring the 1 around, and there you have your c. c equals 3. So the particular solution that we wanted was negative cosine of x plus a 3. And there you go. We could do a similar thing with velocity, position, and acceleration. If I give you, well, first of all, let's review. Remember, we've been starting with position, and once you have position, you can find velocity. How do we find velocity? The derivative of the position. And once you have velocity, we've been finding acceleration, which is the derivative of velocity, or the second derivative of position. This is how we've been going. We're going in this direction. According to the mean value theorem, we can go back the other way. That's the fun part. All right, so if I give you acceleration, they're giving you acceleration right here. The initial velocity, right here, and the initial position. So these are what we call initial conditions, and we'll talk about that more as we go into antiderivatives more. But that's basically what they gave us back here. When they gave us this particular point, it allowed us to find c. Well, by giving us these initial values for these two functions that we're going to be finding, we'll be able to find the particular c value. All right, find the object's position at time t. So they're giving us a for any value t. So this is actually a of t. No matter what, it's 9.8. That's gravity. And then from a, we can work our way backwards by thinking about the antiderivative. So if a of t is 9.8, let's work back. So the antiderivative would be v of t. We'll work on notation of this as we go, but right now we're just kind of doing it with a little bit of hand waving. All right, so what function would I need here so that the derivative would give me 9.8t? I mean, 9.8. Well, let's think back. The derivative of what kind of function gives me a constant? Isn't that something that has a t in it? It's got to have a t, otherwise it would go to 0. So let's just put 9.8t. And we're going to have rules for this, but again, a lot of hand waving here. Let's try it. 9.8t, take the derivative, we get 9.8. There we go. But remember, there's a whole family of opportunities here. So we put plus c to represent all of the possibilities. To find the c, we use the initial value. I suggest you do this as you go. If you don't, you're going to have c, d, e, you'll have a whole bunch of variables to add later. So find them each step of the way. All right, so we know that v of 0 would be 9.8 times 0 plus c, and they told us that that equals negative 5. So with that information, 9.8 times 0 is gone, so we know that c equals negative 5. There's your velocity function. The particular velocity function for this scenario is 9.8t minus 5. Now that we have velocity, we can take the antiderivative of that. We can work back to the function that would give us v as a derivative. All right, well, if I have a t, and I'm going back to the previous function before I took the derivative, I'm going to need a higher power. So I'm going to need a t squared. So let's just try 9.8t squared. And then the same thing as we did before. To have a constant when we take the derivative, we need a t in the previous function. And don't forget, plus c. Now this is a different c, so you could call them something else, c, d, e. But I'm just going to call them c with a little tilde. All right, let's see if this works. Remember, we're guessing, we're hand waving right now. We'll have rules later. So the derivative here, power down. Uh-oh, that would be 2 times 9.8. Well, that's too big. So 2 times what would give me 9.8? What should this be? Well, if we divide it by 2, that would work. So 2 times 9.8 over 2, those 2's would cancel. Give me my 9.8, t to the first power. There you go. Derivative of negative 5t, negative 5. Derivative of the constant is gone. There you have it. This is going to be the position function. But remember, they have given us some information. They have told us what the initial position is. If you plug in 0 for t here, only the c tilde will survive. And they told us that the initial position was 0. So c tilde is 0 here. So that information gives you the final position function. 9.8 over 2 would be 4.9 t squared minus 5t, and c tilde is 0, so it's gone. There's your position function. So if you know your acceleration, you can work your way back to your position. And if they give you initial conditions, you can fill that information in to get the exact formula. All right, that's what I had for you in this section. So study hard, do your homework, and I'll